How many people are online?
2. Okay. So, oh man, that's not it. Slideshow. Set up slideshow. Start window. There we go. Pretty good. Okay, so here is my kinetic energy equation. So, normal kinetic energy is half the mass velocity squared, correct? Okay, here, angular kinetic energy is half the inertia omega squared. Half the inertia omega squared. Okay?
Why are there so many different versions of my equation?
Why is there so many different versions of what?
Yeah, isn't this like the third one?
You think you had to make multiple versions to tell the different substitutes. Okay? So, kinetic energy is equal to half the moment of inertia omega squared. Okay. So checking this out, we're kind of piecing everything we got together. Now, honestly, what makes sense to help, what I try to do, is let's write out all the equations we know. Okay? Let's write out all the equations we know. We have learned, so my kinetic energy, let's write that one out. We just learned that. Kinetic energy is equal to 1/2 inertia omega squared. We just talked about that. Okay? Inertia, we just covered that. Inertia is the sum of the mass radius squared. Okay?
Does that mean like if it's like the sum? Is it if there's two masses, you add two, you square those radiuses and multiply those by the masses and add those two masses together?
So
if there's like two weights, you do mass times radius squared for one.
Yep.
Mass times radius squared for the other.
Correct.
And add those together.
yes.
So should we put
Would
like
the radius
parentheses?
be negative for one of them?
Radius would still be positive.
Okay.
Would we put parentheses around the MR squared? Like,
Yeah.
Make it easier.
So like, for example, mr squared of one mass, and then a second mass would be like that. Right? Okay, so we know inertia. All right, let's see, what else have we learned? So using omega, we know that velocity is omega r, right? Okay. And that should help us out. All right, those three should help us out with these upcoming problems. Okay? So, I'm confident in our ability. Say what? Oh, I thought you did. I was really excited. You did say something?
Yeah.
Oh, what'd you say? I was really excited.
I'm not confident in myself.
That's kind of like opposite of what I just said.
I don't.
This is kind
You
of.
said, well, you said, I'm confident that we can do this, and I said, I'm not.
That's really.
That's actually what I said.
I'm sorry, but I think we can do this.
Okay. You got this.
I don't know why this is really not working.
Has anybody answered the riddle?
Yes,
Doubling. It's always doubling.
it's always doubling.
I don't know.
Why?
Double.
Oh, that's so dumb.
No, it's not. That's a great riddle.
It's not even a riddle.
It's not a riddle, no.
That's a play on words.
All right. All right. So let's check this out. A sphere with the inertia is equal to 2/5 mr squared with a mass of 28 kilograms and radius of 0.38 meters is rotating with a constant angular velocity along the diameter of a sphere. If the kinetic energy of the sphere is 236 joules, what is the tangential velocity of a point on the rim of the sphere? Yep.
Which diameter is it that it's rotated? Is there an infinite number?
What is
A sphere with a mass radius along the diameter of the sphere. Can you say that one more time?
There are an infinite number of diameters of the sphere. So which one is it?
They're all going to be the same.
Yes, but it depends.
Do the
Which one it is.
largest, like the outside. So
They're all going to be the same.
does it
I
matter?
mean, it doesn't matter. No, but if we're trying to find point on the sphere, it does matter.
We're just trying to find the velocity here.
tangential velocity? I don't know what that is.
Okay.
Dimension getting to you?
Huh?
Dimension
So
getting to
let's check this out. All right. So we know my kinetic energy is 1/2 the inertia omega squared, correct? Okay. So here, I know my kinetic energy is 236 joules. They tell me that in the problem. 1/2. Now my I equation, I'm going to put a big parenthesis here. My I equation is said to be 2/5. Let's see, m. So what's the mass? Mass is 28 times r squared, which is 0.38 squared. Times equals omega times omega squared. All right, I wrote really small. I'm sorry about that. Can you all see that okay? Okay. So, what is omega? What would omega be?
I got 17.
I got 17.
I don't get 17.
Wait, you're agreeing?
Yeah.
Wait, is that the dimensional velocity or is that?
Oh,
This
yeah.
is the angular.
That is not what I'm gonna get. I don't know.
Did 8 get 17? I actually
17?
got the correct answer, unlike you guys, which is
All right, so that is the omega. All right, we have to solve for the tangential velocity. So remember, tangential velocity is right here. So that's the equation I'm going to use. V is equal to omega r. V is equal to omega r. So omega is 17. R, my radius, was 0.38. So what's my tangential velocity? 6.5?
I don't know how to work this calculator.
That's a phone.
Is that what you guys are getting?
Yeah.
And that's angular kinetic energy.
Hold on.
That is nifty.
I guess if I was an electrician, I'd say that is.
Have you seen the movie?
I actually just paused.
So what? Yeah, I was gonna say Zootopia. That's have you seen that?
It's
Oh,
better
wow.
than like.
Have you seen the movie Zootopia?
Yeah.
Alright, so there's a guy called Flash 100-Yard Dash.
Oh,
It was so nice.
He works at the.
Not the Spanish. Not the
Mr. Bowers.
I'm good.
Anybody else?
Alright. How do we feel on that example?
That one
Okay.
It's a little too much.
It is. It doesn't hide.
Yeah. How do you think the growth feel?
Yeah.
Okay, so let's check this next one out. All right, so example number 32. From the following diagram, a solid cylinder has a cable wrapped around it and is pulled 2 meters with a force of 9 newtons. All right. Find the cylinder's angular speed and the final speed of the cable.
Can you enlarge the problem by any chance up there?
Absolutely.
You can just put my glasses on.
I have.
We know you're old, but stop being cranky.
I'm not cranky. I'm in a fantastic mood today. Yesterday, I was cranky.
All right. All right. So, find the cylinder's angular speed. All right. So this one's a little tricky. All right. This one's actually a little tricky. And what you have to think of in this problem, can I change off of this?
Yeah.
And move my meeting spots up a little bit. What you have to think about here is work. Okay.
Not as at school.
So, what 2 equations do we know for work? Force?
Force times distance.
Force times, we'll call it, say, displacement. Force times displacement, cosine theta. Okay. What's the other equation we know for work? This would have been chapter energy.
Chapter energy? Work non-conservative.
Oh, is this something with power?
I mean, there is a work and power equation. So power is equal to work over time. Delta kinetic energy, very good. So, what happens? What happens if we have those 2 equal to each other?
Yo, that's kind of whack.
Okay. So, if we put these equal to each other, what's my force in my problem? 9. Okay, 9 times delta x. How far did I move it? 2. Cosine theta, it's just going to be 0. So, or it's going to be 1.
Yeah.
Okay, so times it by 1. I don't feel like putting times 1. Should I put times 1? I'll put times 1. Is equal to the change in kinetic energy. Okay, so change in kinetic energy. So 1/2. Does it tell me what I want to do here? Inertia, let's see. Yep, mr squared. So we're good. 1/2 mr squared. All right. And that's going to be, let's see, solid cylinder 1/2 mr squared. All right.
So isn't it?
We do, it's
Not
50 according to the picture.
just inertia.
Would we also?
Yes, you're right. Yeah. So 1/2 inertia omega squared.
Yeah.
Inertia omega squared. Okay, that was my bad. Minus 1/2 inertia omega squared. Whoop, can't see that. Let me zoom out a little bit. Okay, so there's a start to our problem. Okay,
Why are you subtracting it?
delta KE.
Oh,
All right.
Okay.
So let's solve. All right. So obviously the left side is 18 is equal to 1/2 my inertia. So my initial, or I should say, yeah, my initial.
Would you use the 2 meters?
Why am I struggling? Final minus initial.
I think we should skip this one.
Nope. It's a bad idea.
We will work through our problems.
1/2 inertia. So I know it's kind of hard to read in the top right problem. So I is actually, wow, I got to create a second parenthesis. 1/2 m, so mass. What's my mass? 50 times r squared, which is 0.06 squared. So that's all I.
This is a huge problem.
This is my inertia. So all of this is inertia. Okay? And then omega final squared. Okay? Now, the following solid cable wrapped around it is pulled 2 meters. The final. Okay, so if we actually check this out, what's our initial? Our initial is all 0. So all of this is going to be 0. Solid cylinder has cable wrapped around it and is pulled. So before it's pulled, all of that's 0. So we can just solve for WF right there. I love zeros.
Same.
So I know I kind of drew that up really weird.
As far as you drew it correctly, which is the right way.
So what?
You did it the correct way, which is the right way.
Okay.
This is gonna be really good.
I got around 20. 20?
Oh wait, I didn't. 20 exactly. That's what I got.
Okay. So omega final is 20 radians per second. Okay. The other part, so it says find the tangential speed. So, or find the final speed. All right. So let's find the speed of it. So omega r is equal to my velocity. Okay. So omega was 20. What's my radius?
2.
2. Or it's not 2. 0.6. 0.06.
0.06.
I was like
2 meters.
thrown off a little bit. So that times that is going to be 1.2.
Yeah.
Okay. I want to try one more problem out. That was a little tricky one.
Mr. Bowers?
Yes.
For when it says the final speed of the cable, that doesn't like change, like you go off of the tail of the talking about, it doesn't change like what the radius is. Or what.
It doesn't. Can you say that one more time?
Like does it change like any of the variables that we're using or? I don't know. I don't see.
No.
It's just changing.
No.
Okay. So for like the amount of inertia, you give us the like equation that you just put all the APs and give us the equations.
Oh, I guarantee it. Absolutely. Because some of the problems I chose on AP Central had it. So you should be good. I'll check. I'll double check here in a second. That's a great question. Okay. Let's try one more. Number 33. Do we want to handle 33?
Yes.
We do?
Yeah, why not?
Seems like a fun challenge for a winner.
Oh, gosh, no.
This is a great challenge.
Let's do 34.
Yeah, actually 34.
34.
Yeah.
Conceptual example number 7.
All right,
Let's do all of them.
let's try number 34. Okay, so here we go. Last one for the day. A solid cylinder. Oh dear. You guys know what you just signed up for?
A fun challenge on a Wednesday morning.
A solid cylinder with a mass of 10 kilograms and a radius of 0.7 meters has a string wrapped around it and is attached to a block. The block has a mass of 2 kilograms, and when released, it moves down a distance of h and hits the ground with a velocity of 10 meters per second. Find the value of h. Okay. All right. Here we go.
You don't have to do it.
No, we're doing it. We're already started. I already read it, so I mean, I feel like since I already read it, we counted.
Yeah, exactly. You're already 1% of the way there.
Absolutely.
Yeah.
All right. Do you guys have this picture on your notes?
Yeah. We didn't have the picture for the last one.
We don't have any pictures. I'm taking-
We didn't have the picture.
That's just silly.
We wouldn't have been able to tell the mass, and I don't think we had the radius. So we should have installed it.
Okay, so let's try this out. Okay, I gotta minimize this just so I have space. We're going sideways. All right, ladies and gents, mechanical energy initial equals mechanical energy final. Okay. All right, so let's see. Well, we have, let's see, kinetic energy tangential. Okay. Remember elastic potential energy. Let's see. Regular gravitational potential energy. Let's see. What are you missing? Work non-conserved. Okay. Is equal to. Oh, let's see.
Why would you have energy?
Say that one more time.
Oh, yeah, crossing out, yeah.
No.
Oh, okay, never mind.
Just listing them all.
Gotcha.
All right. Let's see. So we're gonna have elastic potential energy. Let's just get the ones out of the way for now. Energy tangential, but also here we're gonna have kinetic energy rotational.
What?
Got 2 factors here. Okay. Okay. There's everything. Okay. We're good. All right, so reading this problem, the block has a mass of 2 kilograms. When released, moves down a distance, hits h. Okay. So, is there any elastic potential energy anywhere in this problem? How about we get rid of that?
I'm starting to like this problem, Mr. Bellers.
Really? 'Cause that's one that's one thing they're gonna be
Let's
wrong.
see. Is there before releasing the string?
That's all potential.
Is that it's all potential, correct?
Yeah.
So there's no kinetic energy. There's no work non-conserved. It's all potential energy. So we're gonna have the mass, gravity, height on the left side, right? MGH. So all of that is going to equal, well, I'm gonna have both of these values, right? All right. So let's see. Let's start. What's my mass?
10.
Well, or no, two.
Mass would be 2. The block has a mass of 2. So mass is 2. Gravity is 9.8 H. Okay, we're halfway there. All right. So kinetic energy tangential is 1/2 the mass. Velocity squared. So my velocity here said it hits the ground with a velocity of 10 meters per second. So 10 squared. Okay, so there's the first part. Plus, let's do my rotational. Okay, so rotational is 1/2 I omega squared. Okay, so we're going to do 1/2 I. Let's do I first. Okay, so I. So it's going to be 1/2 mass radius squared. Very good. Okay. So we're going to have 1/2 mass. The mass is the final, a solid cylinder with a mass of 10. So the final is going to be the 10. Okay. Final mass is the 10. Okay. And let's see. My R, my radius, 0.7. So 0.7 squared. Okay. So we got all that. And then omega. Does it tell us omega? No. Okay, so we got to find omega. Now, we do know omega. What does that mean? Omega R is equal to velocity. Well, we know our velocity is 10 and we know R is, let me find it, it's 0.7. So what is omega? Really? So you gotta divide by 0.7 on both sides?
My calculator's in the wrong mode.
It'd be 11 and 14.
Makes sense.
No, no.
It's 14.
Now it's 14.
Is it 14?
Is it 14?
Yeah.
Okay, so I'm gonna have 14 squared, because that's omega squared. Does that make sense where I got all those numbers?
Surprisingly, yes.
So plug this all in your calculator.
What was that? We can solve for,
All right, so let's do 150. 100 plus.
Yes, there's one sig.
It's 1?
Yeah.
It's 17.
Oh, because of the 2. What is it?
how did you guys do?
1. You know, because
All right, so ladies and gents, I got a height. Before sig figs, I got around 17.35, 17.4. After sig figs, it would be 20. We gotta end on that one. We gotta end on that one. All right. So, energy. We got to use all the energy equations we know and apply them this. How do we feel? We good? All right, we're almost done with this chapter, which is kind of crazy. Tomorrow, like I said, I will not be here. So, I assigned those problems. Try your best, like I said. Gave you guys some doozies. A little challenge. Challenge for the mind, the body, the soul, you know? But you guys will do good. And then an easy lab on Friday. Or maybe we should just have like a movie day.
Oh, yeah.
Tommy's not gonna be here.
We should watch Die Hard.
We should watch Die Hard. We should watch Tenet.
Yes. It just came out on DVD.
Just on repeat.
Let's watch.
What? What did you say?
You can watch the walk.
Yeah. Okay.
Landon, are you muted?
Yeah.
I love that for you.
Oh, I was looking at the picture. I was like, I was watching the video. I was like,
Did you paint it with Sharpie?
No. Yeah. Someone said that I wouldn't do it. And guess what? Oh yeah, no, my first time. Did it at 9:30.
It's kind of interesting. So
when I got back from the, I'm like,
I said to myself,
you have them on my heart. You have the CGs or the all you need is that having an internet.
Yeah.
Yeah, no, I'm not touching that.
Yeah.
I wash my hair and head first.
So juniors are black.
It's like the food is black, which looks more like the like ours super.
So I have a lot of freshmen, so last period was blue.
Yeah.
But my first period, it's my chemistry class. They're mostly juniors, but
Yeah, but it seems like it was those.
man, I couldn't tell what they were. Like,
Neon?
no,
Oh, tomorrow
No,
we're doing all that.
There's a lot of juniors that just didn't.
Yeah.
Like, you get the easiest one, like,
And they still did.
I'm upset they're not gonna see
Or
my
black every day.
what
I
I'm doing
know.
tomorrow.
Don Gray wears
I'm
black
going
every day,
all out.
and he wore red today.
Can you take a picture?
Tomorrow,
You gotta see
Tomorrow,
me.
Dude, I have an 8.
Listen, I was gonna spray my hair gray, but then I was like, yeah, I really wanna wash my hair
don't
tonight.
go that far.
I'm totally.
Don't do what I did. Don't take it too far.
You should.
You're your favorite character tomorrow.
It's actually medium gray. What?
Where's the rest of us from?
I gave it
See you guys. See you Friday.
No, I was not a fan.
See Mr. Bowers.
See ya.
He was kind of.
to the I should have got a head start.
Attention all current teen mentors. You will be going to Dennis Elementary today to see the Borough Buddies, socially distanced outside. Even if you do not have a buddy, you are still welcome to go.